Hello, remember that we can analyze a gas by keeping track of its states, meaning its pressure, its volume, and temperature. Now, is there a graphical way to present changes in the states of a gas? So look here, I have a cylinder of gas. If I attach a whiteboard to the piston, then as the gas contracts and expands, the whiteboard will also move right and left. Now, if I attach a pencil to the needle of a pressure gauge, then as the pressure of the gas goes up and down, the pencil will also go up and down. So do you realize that as we play with the gas, as its pressure and volume changes, a trace will automatically be traced out on the whiteboard, showing the changes in pressure and volume of the gas. So this thing is called the indicator diagram. Apparently this was invented by Watt and his assistant. Today, of course, we have data loggers and everything and computers, but nevertheless, we usually use a pressure volume graph to keep track of the changes in a gas. So take for example, if you see on the PV diagram, that's what the indicator diagram is also sometimes called. So if you see a horizontal line, what are we looking at? So this is an isobaric expansion. It's a gas expanding at constant pressure. So between state A and state B, which one has the higher temperature? You say, hey, this is a PV diagram, only shows pressure and volume. It doesn't show the temperature, how will I know? Remember PV is equal to nRT? The P times V here is definitely smaller than the P times V here, right? So this must be lower temperature than this. Nevertheless, we see your point that no, temperature is not shown obviously on the PV diagram. So quite often you see these lines drawn on the graph as well. So these are called the isotherms. They are lines joining all the points which are at the same temperature. Meaning along this graph, all the P times V is equal to nRT1. You can draw another isotherm here. So at every point along this isotherm, P times V is equal to nRT2. And it's very easy to tell which isotherm is at a higher temperature. The one higher up is the higher temperature. So T2 is higher temperature than T1. Now very often during exams, we make you calculate the pressure at B. And very often it will involve Charles's law, because at constant pressure, V1 over T1 is equal to V2 over T2. So the gas is currently at state B. Suppose now it undergoes this thermal process to go from B to C. Now can you tell me whether the gas is hotter now at C compared to when it was at B? No, right? C and B are at the same temperature because this process took place along this isotherm. So in fact, this is called an isothermal contraction. Not only it started and ended at the same temperature, it remains at the same temperature throughout. If we were to make you calculate the pressure or volume at point C, usually it will involve Boyle's law, because at constant temperature, P1 V1 is equal to P2 V2. So we are now at state C. So suppose the gas is brought from state C to state A along this vertical line. So can you tell me whether going from C to A, has the gas cooled down or become hotter? Yeah, cooled down, right? You can clearly see that it went from a higher isotherm to a lower isotherm. Or it's obvious to you that the P times V here is higher than the P times V here. In fact, if we were to ask you to calculate the P and the V here, usually it involves, what is this law called? Guy-Lussac's law. Because at constant volume, P1 over T1 is equal to P2 over T2. Okay, now I would want to talk about work done. Going from A to B, this rectangular area here represents the work done. Work done by who? It's an expansion, so the gas did the work. So the work done by the gas is represented by this rectangle here. Alternatively, you can talk about work done on the gas. If you are talking about work done on the gas, then the work done on the gas is the negative of this area. Okay, what about during process B, C? So again, there's a change in volume, so there's work done, represented by the area under the PV graph. So this time is a contraction, meaning the external environment, the surrounding, has managed to compress the gas. So this time around, work is done on the gas, and the amount of work done is represented by this area under the graph here. But if you insist on talking about work done by the gas, then work done by the gas is negative, because the gas tried to push outward, but instead it got pressed inward instead. Now what about during process CA? What is the work done by the gas or on the gas? Notice this time there's no change in volume, so work done is 0. Easy? Now just to briefly mention this thing, you notice that the gas was brought from state A to state B to state C and then back to state A. This is what is called a cyclic process. And in a cyclic process, the area enclosed by the loop represents something meaningful. But before we talk about that, I'd like to introduce you to the first law of thermodynamics first. So see you in the next video. Ta-ta!